of flash photolysis, with Professor Sir George Porter describing his development of the first flash apparatus. Here's Dr. David Roberts of the Open University to present today's programme.
The absorption of light, the first event in any photochemical change. So one of the important things we need to know about a molecule when studying its photochemistry is its absorption spectrum.
Just put it in, and away we go.
This is simply done these days. It just involves measuring the fraction of light shining on the substance that's transmitted at each wavelength. The absorption of a photon excites the molecule from the ground state to a higher energy level. For most organic molecules, the state formed by direct excitation is a singlet excited state. But there are others, called triplet states, that can be formed by a process called intersystem crossing. What happens to these singlet and triplet excited states is the next event in any photochemical process. The question then is, how can we study the fate of such excited states? Professor Sir George Porter.
Generally, the excited state, which is first formed when a molecule absorbs light, exists for less than a millionth of a second. So the chemist who studies excited states has to be a pretty fast worker. He has to have some method for studying reactions in less than a millionth of a second. Well, fortunately, such a method exists. It's called flash photolysis, and you'll be hearing a great deal about it in this course.
The most coveted prize in chemistry was awarded for the development of the technique of flash photolysis. At a ceremony like this one, Professor Porter and his former supervisor at Cambridge received the 1967 Nobel Prize in Chemistry. Flash photolysis was born in an attempt by Professor Porter, then a research student at Cambridge, to measure the spectrum not of an excited state, but of a short-lived molecule called the methylene radical. The problem was how to do it.
How did you first come to the idea of using a flash of light to initiate the reaction?
I started with a continuous mercury lamp. Actually, I started with a carbon arc, which was an old army searchlight. And then we wanted to get more ultraviolet light. So we used a 7-kilowatt mercury lamp, which was very intense indeed. In fact, I got a nasty bout of conjunctivitis one night through not being well protected from this. Well, this lamp didn't have a very long lifetime. It soon blew out, and I had to go and get a replacement. And I went to Siemens Lamp Works in Preston. And there, since I'd gone all that way, they showed me around their works, and they showed me some flash lamps. In fact, they were long flash lamps like this, about 1 meter long, filled with inert gas and with heavy electrodes at either end. And these had been used during the war for aerial reconnaissance. And everything clicked. The flash lasted about a thousandth of a second, which I knew was the lifetime of methylene. The intensity, the amount of energy in the flash was enormous. And when I went back that night to my hotel, the station hotel in Preston, and there wasn't much else to do except think in the station hotel in Preston, I, on the back of an envelope, calculated the energy and the requirements, And it all seemed just the answer, and it was.
How was the flash with such a short lifetime produced?
Well, one discharged condensers, capacitors through the lamp, and a lamp of that kind was alleged by Siemens to be capable of taking about 10,000 joules, which is a lot of energy. And so one took condensers like this and put something like 500 or 1,000 of these all in parallel, charged them up, and hoped that they would stay charged, not blow up, and discharge them through the lamp in one go. Actually, the condensers were, of course, the biggest item of the apparatus that I had to get together. There wasn't much apparatus around. This was just after the war. But I was fortunate that I'd just come out of the Navy, and I knew that the Navy used these condensers a great deal for their radio apparatus, and I phoned some of my friends and said, send me some condensers which you're not using. And they said, we have lots. How many would you like? And I said, all that you can provide. So lorry loads of condensers began to arrive in Cambridge, and Professor Norris gave me a whole room to put these into. We connected them all together. There were a motley lot of condensers, and from time to time 999 condensers would discharge through the 1,000th condenser, splattering the place with tar. But eventually we managed to eliminate the bad ones and get a very large flash, which then blew up the tube, of course. And so we discovered we were trying to be a little too ambitious, and eventually we settled for rather less energy.
What reactions did you study first?
The very first reaction that I studied was I put acetone in the tube because, well, you would just get that out of a bottle, and it was easier than looking for the methylene radical. I looked for the methyl radical with acetone. And the tube, and alongside the flash lamp, you see, was a reaction vessel, something like this. The two were alongside each other, and the whole lot had reflector around it. The problem, of course, was to record the spectrum in 1,000th of a second, or less. Well, I wasted quite a long time, I suppose 6 months, 9 months, being too ambitious again. So eventually I hit on it seems a terribly simple idea, but I'm perhaps simple too, because it took me a very long time to come to this. But the answer was to have a second flash lamp. This is one design. It's not quite what we used in the first place. But instead of this very long one, you now have a little point source. You, again, discharge a condenser across there, get a little point, almost point source, well, not point, but a centimetre, so it's about the same as the slit of the spectrograph. And if you put that on one end of this reaction vessel and your spectrograph the other end, and you make this go flat, bang, and this one, bang, a millisecond later, then you get the whole spectrum, and that's really good information theory, because you are using a very high intensity for the recording during the very time that you need to make the recording.
Those basic components, the photolysis flash, the spectroscopic flash, the capacitors to fire them in sequence, and the spectrograph, haven't changed even in the most modern version of the apparatus, like this one here. The heart of the apparatus is this, the cell compartment. Inside is the sample tube, and lying alongside are the two photolysis flash lamps. Each flash lamp consists simply of a quartz tube filled with xenon gas, and with electrodes at either end. The electrodes are connected to this bank of capacitors, and these are charged by this high voltage power supply, up to around 10,000 volts. Then, all I need to do to fire the flash lamp is to push this knob. The capacitors are recharged automatically each time, ready for the next experiment. Now remember, the flash forms the excited state whose spectrum we want to measure. To measure that spectrum, we need a second flash lamp, the spectroscopic flash, and that's here. Inside is just a smaller version of the photo flash lamp. Like the photo flash, the spectroscopic flash is also fired by a bank of capacitors. But there's one very important difference. The spectroscopic flash is fired after a preset delay once the photo flash has been fired. I can adjust the delay to be anything from 1 microsecond all the way round to 1 second. If I adjust that delay to 1 second, you'll be able to see how that works. Photo flash, spectroflash. Photo flash, spectroflash. You can see the two flashes on this oscilloscope screen. In this experiment, which I did earlier, the delay between the photo flash and the spectroflash was 100 microseconds. You can also see the duration of the two flashes. In each case, it's about half a division, about 10 microseconds. What else do we need? The final component is the spectrograph. This disperses the light transmitted through the sample. The spectrum is then recorded on Polaroid film. The film holder can be moved up and down so that up to 8 spectra at different delay times can be recorded on one photograph. I'll take the film holder off so that you can see how that works. This is the exit aperture. The light passes through this and onto the Polaroid film. So each spectrum appears as a narrow strip, the same shape as the exit aperture, with each one covering the whole spectral range of interest. To summarize then, the sample sits here beside the photo flash lamp. The cell compartment is next to the spectroscopic flash lamp. Light from the spectroflash shines through the sample and into the spectrograph. The spectrum is then recorded on photographic film. So, let's do an experiment. I'm going to measure the absorption spectrum at the lowest excited triplet state of naphthalene. Now you remember, in the previous program, you were able to see the absorption of an excited state with the naked eye. But there, the compound was embedded in a solid plastic rod. In this experiment, I'm going to measure the naphthalene spectrum in solution. In solution, the excited state absorption lives for a much shorter time. The solution's in this reservoir because it's been carefully degassed. Otherwise, dissolved oxygen makes the absorption disappear even more quickly. So the first thing I have to do is to tip the solution into the cell. I've already measured some of the spectra, so for this one, I'll set the delay at 250 microseconds. Open the shutter and fire. Move the film holder down 1 notch. The delay at 300 microseconds. And fire. Well, that's the last one. All I have to do now is to develop the film. And here's the result, a series of spectra taken at different times. This one after 20 microseconds, this one after 40 microseconds, and so on. Note that the wavelength scale increases in this direction. What we have then is a series of spectra showing the decay of the naphthalene triplet state with time. So, by looking for this characteristic pattern of absorption, processes involving triplet naphthalene can be followed using flash photolysis. But what about the excited singlet state? Can flash photolysis be used to monitor its reactions? Typically, excited singlet states in solution have lifetimes of tens of nanoseconds, as opposed to tens of microseconds for triplet states. So the type of flash lamp we saw earlier, which is limited to a minimum duration of about 1 or 2 microseconds, is too slow. Instead, we have to use a pulsed laser to produce the flash, like this neodymium laser at the Patterson laboratories of the University of Manchester. It produces light of wavelength 1060 nanometers, which lies in the infrared. By passing it through 2 successive frequency doubling crystals, ultraviolet light of wavelength 265 nanometers is produced. Here at the Patterson laboratories in Manchester, Dr. Edward Land is aligning the laser. By adjusting the lens, he ensures that the laser pulse is focused onto the sample cell. The sample is degassed by bubbling nitrogen through the solution. This removes dissolved oxygen. For this experiment, a solution of naphthalene in cyclohexane is used. The degassed solution in its reservoir is then ready to be attached to the apparatus. The sample cell has an inlet and an outlet. Nitrogen gas pressure is used to push the solution into the cell until excess emerges through the exit tube. Unlike the experiment I demonstrated earlier, this apparatus monitors the transient absorption continuously at a single wavelength. The monitoring light intensity, I0, is checked. Now we're ready to fire. The transmitted light passes through a monochromator and onto the detector. The signal is displayed on an oscilloscope, and the resultant decay trace is recorded on Polaroid film. This curve is a measure of the transient absorbance at 416 nanometers. A fresh sample is used for each run. The wavelength is set. The monitoring light intensity, I0, is checked. The laser is flashed. And the result? A decay trace for 418 nanometers. Again, fresh sample, adjust the wavelength, check I0, fire the laser, and the result. A complete spectrum needs at least 30 or 40 such photographs. For each photograph, the coordinates of the decay trace are fed into a desktop computer. The computer then analyzes the complete set of decay traces and produces a spectrum at any given delay after the laser flash. This shows the naphthalene excited state absorption 20 nanoseconds after excitation, which is mainly due to the excited singlet state. Note that because of interference from naphthalene fluorescence, it wasn't possible to take measurements below about 390 nanometers. At 100 nanoseconds, the singlet state absorption has partially decayed away and is overlapped by absorption due to the triplet state. At 700 nanoseconds, the triplet absorption has completely replaced the singlet absorption. At progressively longer times, the triplet absorption then simply decays away. So, by using a laser source, singlet and triplet excited states of a molecule can be monitored. In the experiment you've just seen, each decay, both singlet and triplet, produced a separate photograph, the data from which had to be painstakingly read into the microcomputer. It's simpler and quicker when a large number of runs are involved to record the data direct by attaching a computer to the flash photolysis apparatus. So now we'll give you another opportunity to see the experiment, but this time with data processing equipment connected to the apparatus.
Let's see what we have. Can you give me a laser flash?
Here, Dr. Land's colleagues, Professor John Baxendale and Dr. Stephen Atherton, are aligning the laser to carry out a similar experiment.
That seems okay. Let's put the reaction vessel on. Line up the optics. There. That seems fine. Put the lens on. There. Let's just check the laser beams on the lens. Okay, Steve. Another one, please. Yeah, that seems fine. Let's check it on the vessel. Okay. Yeah, that seems fine. Let's have some solution. Thank you. Well, the light seems okay, Steve. Let's start at 4.
As before, the data are collected one wavelength at a time.
Okay, I'd like to check I naught.
Okay. I'm firing now. That seems okay.
But this time, the data are fed directly into a computer.
I'm going to fire again.
Right. That seems all right, yeah. I'll take that one, yeah? Okay?
Yes, that's fine.
Okay, let's change to 418 now, shall we? 418. Okay, go.
That looks fine.
That's okay?
Okay, should we take
Let's
it?
go, yes. Let's change to 420. Okay, go.
Firing now.
Good. That's
Okay,
fine.
so-
That's all that. 422. Set. Put 2 nanometers.
Firing again. Yeah, I know.
Okay, yeah. Take it.
Firing now.
Okay, yes?
Yes.
Fine, take that one, yeah. Okay.
I know.
Yeah. Okay.
And now we come to a program for students taking the science faculty's second level.